Okay, I'm ready.
Okay. Hi, everyone. Well, welcome to our discussion of the day with Jim Gates. We will be talking about physics and adinkras and supersymmetry and all kinds of things, I hope. And so Jim, I'm trying to remember. I think you and I first met probably in 1980. Does that
That is
sound
correct. That's actually right, Stephen. I actually remember that meeting. I was a new postdoc at Caltech, and you were this hotshot graduate student.
Okay, right. Okay, I'm now you're going to embarrass me because I don't know what happened in that particular meeting.
But nothing untoward. I mean,
oh, that's good.
It's just that so I was a postdoc, and there were a bunch of us postdocs and graduate students. And then someone said, "Have you heard about Stephen?" And I'm like, "No." And they said, "He's really, really smart." Okay. So that was the first thing that's the first things I heard about you.
Okay, that's may not be the best introduction. I remember that you had a collaborator at that time, Warren Siegel, is that right?
Warren Siegel, absolutely.
Right, and I always used to, it was like there was this somehow, one tall guy, one short guy talking about supersymmetry.
Yes, that's exactly right. There's this movie called Twins with Arnold Schwarzenegger and Danny DeVito. And so we were kind of those twins, except one of us was African-American, the other was European-American. So it was kind of an odd twin.
But at that time, you were already interested in supersymmetry.
Absolutely.
How did you come to supersymmetry? What was that story?
Thank you for asking that question. Often I have to get by a graphical talk, so this is a central element. People ask this question. And so I was a graduate student. I started graduate school in 1973 at MIT. And I'm the first person in my family to go to college at all. And so, it was interesting undergraduate experience. I had been an undergraduate at MIT. I double majored in math and physics. I was having the time of my life as a student. And then graduate school came along. And my grades were okay. I didn't have problems passing. Well, I didn't have problems getting good grades. I was never a good test taker, by the way. I tell students all the time, don't worry if you can't take tests, because that doesn't measure what you actually know. But when it came time to do a thesis, I had already started reading the physics literature, and I noticed that when the preprints would come in, there would be lots and lots of papers on what people were then working on is what we now know the answer to, which is SU2 cross U1. But in those days, no one knew the answer. So there were people trying to write weak interaction theories based on SO3, SO5. You just pick your group, right? And then try to put together a description of the weak interactions. And so my advisor, an African-American gentleman by the name of Edward Young, had been working on one of these extensions of the standard model. The model he had worked on with some collaborators was SU2 cross U1, where the second SU2 was actually gauging flavor. So,
okay.
I'm sorry, gauging family number. So it's sort of horizontal versus vertical.
Okay, so but we might have almost had family-ons.
That's right. It might have had family-ons, and that's what he and his research collaborators had established. And so I was studying this stuff, and I was looking and trying to figure out what kind of thesis I would write. And most people don't know this, Stephen, but I started out as a weak interaction phenomenologist. If you look at my publications, the first two publications are about weak interaction phenomenology.
Okay, so there's a piece of trivia for you. You may not have known that was the first area that I worked on as well, was weak interaction.
I did not know that.
Okay, so what were your first couple of papers about?
So in the context of this model, that my advisor, along with a physicist named Vigdor Teplitz and Dwayne Dicus.
So I remember those guys. Yeah.
Yeah. Mm-hmm. So my advisor had worked with Vig and Wayne, and they had put together this model where you, like I said, they gauge flavor. And in their paper, they had not looked for the most general scalar potential, because they had a spectrum of spin zero fields to the Higgs, and so that had been left unsolved. And that was the first piece of research I worked on, was trying to figure out how do you classify the general potential given the Higgs representations of the Higgs fields that they picked. And so I solved the problem, and in the process, I accidentally discovered something called the Michel parameter, which I didn't know Was
That's
it
like
known?
rho, the thing for the muon decay.
Yes, that.
See, I
So,
still remember my particle physics a little
well,
bit.
apparently so, if you can pull that one out. And so like I said, I was having fun, but then I was like, I looked around at all these professors are writing papers and postdocs, and I'm thinking, I'm just a young graduate student. How in the world am I going to be able to compete against these people with 10, 15, 20 years of experience? And so at that point, I decided that I was going to do something different. So I had a plan. The plan was, in those days, of course, the literature was much smaller than it is now. So the plan was to go look at all the literature on particle theory, classify what people were doing. So there was a bag model, for example, for hadrons. There was the dilute gas approximation to QCD. There was working instantons, right? So these are all the buzzwords that, when you and I were in kindergarten, these were the buzzwords we heard, right?
Yes.
So I looked at all these things. I looked at the authors. I looked at the institutions where this work was being done. And all of it, in this search, I found one or two papers by Abdus Salam and John Strothby. There was also some work by Vessin Zimino, Sergio Ferrara, and they had this strange theory called supersymmetry. And so I began to study it because the mathematics, at least in the way that Salam and Strothby presented it, was unlike any mathematics I had ever seen as a graduate student at MIT. And so after about 2 or 3 papers in phenomenology, I decided I was going to switch and start working on supersymmetry. My advisor, remarkably enough, did not object. And so I started studying it. And I pointed out to him, by making this choice, I could become an expert because I could master all of the existing literature. And therefore, you could get to the boundaries and start answering questions that nobody knew the answers to. And so that was my philosophy, and that's how I got into supersymmetry.
I really like that strategy. Have you passed on that strategy to generations of students about how to pick your research area?
I tell all my students know this story. I tell them that one of the things that if you're a young student and you want to try to take the best opportunity to have a long career, you have to distinguish yourself. And it's really difficult to distinguish yourself in an area where some of the world's smartest people have been working for decades. So you need to try to find something new, but you also have to have what I call a sense of aesthetics. Because as you know, Stephen, in the field of particle physics, ideas come and go. They're basically, they're fads. An idea will pop up, it will be popular for a while, and then it will disappear as if it never existed. So the trick is find something new, but you have to have an internal sort of compass about what is your best guess about something that's going to be really important. And in my case, that compass pointed to supersymmetry. And that way, by the time I got my PhD, I was the only person at MIT who knew anything about supersymmetry. So this is like 75, 76. And 77, because I graduated in 77.
So was that, just to ask you about the Salam strategy, I sort of vaguely remember that. Was that mixed up with their preons business, or was that a completely different branch?
It's completely different, but they did do work on preons, but it's the same research team, exactly.
Okay.
So
what got them into, why did they think about supersymmetry? Was it just Salam thinking about kind of symmetry groups and where they would be different places to apply them, or what?
So, you're familiar. So Abdus was a very interesting guy because he worked on all kinds of symmetry groups, as you mentioned. There's stuff on that. There's some work that he did that looks remarkably like ADS-CFT that most people have forgotten about. But if you're old as me, you remember these stories from the old days. And so he was someone who definitely was interested in symmetries. He worked on models, for example, of 2 graviton type models, but in the context of what we now would call QCD as opposed to fundamental gravity. And so, as far as I can tell, his interest in symmetries likely led him to the results of Vessin Zimino, because the work of Vessin Zimino preceded his work in the temporal order of things. And so Vessin Zimino, they did the so-called Vessin-Zimino model. They showed that supersymmetry could exist outside, independent of string theory. And so, as far as I can piece the story together, Abdus and John read these initial papers. And if you look at the initial papers, it's like looking at special relativity, but writing everything in terms of X, Y, Z, and T, which is not the most efficient way to do it. The most efficient way is to figure out what's the geometry behind the symmetry, find the natural objects with respect to that geometry, and then express the equations in terms of those objects. And so that's what, as far as I can tell, led Salam and Strathy to the idea of superfields and superspace, where superspace is the analog of Minkowski space for relativity.
But so actually, I'm just a piece of particle physics history that I'm curious about, because I met Abdus Salam a few times, and he was he was obviously back in the old days. He was particularly famous because what's now called the Standard Model used to be called the Weinberg-Salam model.
Right.
But I kind of wonder, particularly from what we're saying here about symmetries, it's like, okay, he had a SU2 cross U1 for the Standard Model. He had other kinds of, I'm kind of wondering to what extent he was like a person of all groups, so to speak, where one of them happened to be the winner.
That could well be the case. About a month ago, I gave a talk about my relationship to Optus, because most people don't know that I spent something between 3 and 5 and 6 consecutive summers at ICTP.
I see. Mm-hmm.
And the first one was around the time that you met me, because I got an invitation to come in to a conference. People were interested in supergravity. I was just, this young researcher who had done some work with Warren Siegel. And Warren doesn't like to travel, but I don't mind at all. And so I went to ICTP, and it was probably 1980, like I said, about the time that we met, maybe 79, 80, something like that. And he took an interest in me. I actually, about a month ago, talked about my relationship with Abdus, and it's on the ICTP website. It's actually at YouTube if anybody's interested in hearing the story, because he's actually the first physicist who challenged me to think about diversity in terms of ethnicity. And so that was a very interesting sort of discovery for me. And
that's interesting.
It has consequences that have reverberated to this very day in my life.
Huh. So was Abdus a very high math kind of person, or was he more of a physics type math person?
I would classify him as more of a physics math type person.
Uh-huh.
Although how he and John got to superfields, I will never know. I've been trying to figure that one out, because remember, the data is, you've got the work of Wessens-Zumino. The output is this whole new concept of superspace, which is the analog of Minkowski space. How they made that transition, I can't figure out. I've been looking at this and thinking about it a long time. But he was certainly someone who was, I would say, he was a physicist who was comfortable exploring unusual mathematical ideas. That's how I would characterize it. But that, so, yeah.
Like Grassmann variables, non-commuting variables. That was, by the time I was doing physics, that was sort of a thing one vaguely heard of, but they were not a well-known concept. I mean,
they were not. Although the Russians, they were known actually behind the Iron Curtain, because Berzin, the Russian physicist, is actually the person who first figured out how you perform integrals over these anti-commuting variables.
Oh.
So the part about supersymmetry is really weird historically. It actually has two separate origins. One of them, which we in the West know, starts with Wessens-Zumino, and actually comes from first generation of string theory, because the symmetries of supersymmetry was observed as a symmetry first in the context of string theory by a French physicist by the name of Jean-Luc Gervais and Bunge-Chiquita. And so, coming from string theory, Wessens-Zumino figured out that supersymmetry could be a property that you could realize in terms of field theory. But behind the Iron Curtain, as it was called in those days, supersymmetry sprang full blown from two Ukrainian physicists. One of them was named Galfon, and the other was Lichtman. And what they did, which is truly amazing to me, again, these are people studying symmetry groups. Mm-hmm. And so what they did was, first they figured out how to avoid the Coleman-Mandula theorem, which says that you can't mix internal symmetries with space-time symmetries. But they figured out how you could. And the way that they did that was by essentially writing the supersymmetry algebra. And then once they had the algebra, the next thing they did was to write a paper where they fully write the supersymmetric extension of QCD. I'm sorry, QED. And so there's this whole separate birth of the ideas, totally independent of the Western track.
But so those guys were doing field theory. They were not doing like condensed matter physics.
Nope, they were doing field theory. And by the way, the terrible thing about it was because they invented this new idea that was so radical, no one had ever seen it. Neither one was ever really able to have a very long and productive career in theoretical physics because of that.
Interesting. But so, okay, so Salam, you get sort of pulled into the kind of supersymmetry world and this idea of, so who invented, I mean, the superspace idea of kind of, you've got sort of coordinates of space that are commuting, ordinary numbers, and you've got Grassmannian coordinates of space. Where did that, I mean, one thing that's very confusing to me, I think there's a different thing called superspace that people like John Wheeler were talking about.
There are actually numbers of things called superspace. There's one in general relativity. There's also some superspaces in other parts of physics. But the one that Strathy and Salam created was, I'm not aware that it ever had I'm not aware of a predecessor of their particular version any place in the physics literature. So I think they did something unique when they created their version of superspace, which, as you said, the idea is that some of the coordinates of this are numbers, but the other coordinates of the structure are not even numbers. They're just these weird anti-commuting things.
Right. And so now you've spent a very long time figuring out the implications of that kind of idea.
Well, Stephen, I would say I am still in process, because it's a radical idea and a lot of people have worked on it. But for me, the problem is that if I tell you SU2 or SU3 or pick any compact group, because you were working with these things when I met you as a graduate student at Caltech. So I know you know this stuff. So for ordinary groups, there's a mathematical theory that tells us every single possibility. It's a theorem essentially by Cartan, who classified all of the compact Lie algebras, right? That mathematical result does not exist for supersymmetry. And in fact, that's why I actually start working on Adinkras, because the ultimate quest is to reach that level of comprehensive understanding about the nature of this thing we call supersymmetry. And in 40 years, it hasn't yet happened yet. I'm one of the few people who actually is worried about this, because most people don't worry about this. But as I said, it's rather remarkable that we're not there yet.
So let me understand. So I mean, in the case of compact Lie groups, there is this classification theorem that says there's a certain set of classes, the SO, SU, et cetera, and the exceptional groups and so on. And that was figured out by Cartan, and you get these Dynkin diagrams that represent these different possible kinds of Lie groups and Lie algebras. Correct. And what you're saying is, and obviously in other areas of group theory, there's been a big adventure trying to actually classify the groups. Like in the case of finite groups, that was finally done. If you go to semi-groups, for example, nobody knows anything about the classification, so far as I can tell.
Right.
What you're saying is that in the case of these what do you call these?
Supermanifolds.
Okay, so this is the symmetries of supermanifolds. Is this like the symmetry groups of supermanifolds?
Yes.
Do they have a name like supergroups, or is that?
Well, it turns out the word supergroup actually has been applied to something else.
Oh dear. Okay.
So if you look at the mathematical literature, there's something mathematicians call supergroups, but essentially what they're talking about are the analogs of compact groups, whereas what's necessary to do field theory is a theory of representations over non-compact supermanifold, whatever non-compact means in that context, right?
So but the non-compact is like SO31.
That's right. That's exactly right. That's the sense I mean by non-compact.
I see. But so in the case of, I mean, to ask a naive question, in the case of the Lie groups, is the classification theory of which SO31 is an example? Are those classified, the non-compact Lie groups where they have different signature and so on?
You know, it's a very good question. I'm not an expert, but I believe the answer to that is yes, because of precisely what something you just said, namely that as far as I can tell, if you look at the non-compact group and ask about classification, there's certainly a large group of them that you can get by changing the quadratic form on the space. So you go from Euclidean metric to some kind of Minkowski metric. We know that all of those representations go over. In fact, we use that fact all the time in physics. I've never heard anyone say that that fails.
Right. But I mean, the representation theory of the Poincare group, for example, is an elaborate, I mean, you know, it lives on top of the representation theory of SO3 and things, but it has its own extra tentacles and so on.
That's correct. And that's what I was referring to.
Right. But so okay. So then I'm noticing on our chat here, David is saying that inner versus outer automorphisms apparently classify non-compact real forms of Lie algebras. Okay, so there is some kind of classification there.
Yeah. Okay. Great.
So then, but okay, for the case of these supermanifolds, what you're asking is, if I understand correctly, I mean, kind of what's the analog of something like the rotation group for a supermanifold?
Yeah, well, yes, that's exactly right. What I'm really asking, and in fact, this is what I'm researching is. So let me put it this way. The reason that compact Lie groups is so comprehensively understood is because of the ideas of the what's the words I'm looking for? The Chevalley decomposition of the generators into commuting and non-commuting, commuting subgroup.
Yes.
Then the non-commuting generation. That lets you construct basically a kind of a crystal, a polytope. We call these things weight spaces. But as far, you know, colloquially, you can say because of that decomposition, we know how to construct mathematical crystals. And it's the symmetries of these crystals that govern the behavior of the groups.
So let me just try and remember that. I mean, so this is, you're talking about the center of the group where there are a set of commuting generators.
Correct.
And those give you, in physics terms, kind of quantum numbers that allow you to look at, to sort of draw, like back in the day with SU3 and things, you would draw this, you know, these octets and decuplets.
Yes, that's exactly what I'm saying. And I am looking for that type of construction in the context of space-time supersymmetry, because no one in the world knows how to do that.
Right. So okay. So but in the case of in the case of something like SO3, we know that the representations of SO3, they have an interpretation in terms of successive angular momenta, you know, successive spin values and so on.
Yes.
I'm curious first in the supersymmetry case, when you're looking at these successive representations and so on, is there, and sort of a naive question, maybe I should know the answer, but what's the interpretation? What's the analog of this? You know, what's the thing like angular momentum that classifies those representations?
So you're asking for a set of Casimirs, and that's part of the problem. We don't know. And I don't know anyone that I've ever talked to this problem who's been able to present me with an answer.
I see. So okay, so then there isn't. So the Cosmere invariants are usually these things that are things like the angular momentum or the spin or whatever. And are there any known such things for these?
There are some partial Casimirs known, but the problem is that they don't actually classify the representations. So, for example, if you look at some of the literature on supersymmetry, you will find that there's a supersymmetric extension of the Pauli-Lubansky tensor, for example, which is a tool that's used often in talking about conformal symmetries on manifolds. So there is an extension of that object, but that's probably the only one. And if you try to use that to classify representations, you find out that many representations actually have if you think of a quantum number associated with that thing, many representations will have the same quantum number. Therefore, at best, it's a partial list of operators that you need for the classification.
So let's come to your Adinkras. Am I right in thinking that your Adinkra diagrams are a little bit like those octet diagrams and things?
You're more than a little right.
Okay.
Stephen. In fact, I recently gave a talk. Since we've been talking, I've been sitting here saying we're probably going to wind up talking about the work I'm actually doing now, because it is highly tied to the set of the discussion we've been having for the last idea. The only problem is I've been sitting here searching for a PowerPoint, and I've been failing so far. But let's keep talking.
Yeah, we can just talk.
I'm going to keep searching because I'd like to come back. You've actually touched on a very key point of my research here. So let's go elsewhere, and I'll come back to this.
Right, but so in in a sense, I mean, the diagrams you're drawing are essentially, as I understand it, sort of in the case of something like the SU3 octet. There are two quantum numbers, and you can just draw that on a standard, in a standard diagram. But in the case where you have, you have relationships. I mean, okay, in finite groups, we have things like Cayley graphs, which give you relationships between, graphs that give you relationships between elements of, and how, again, what is the relationship between kind of what, I mean, your graphs are something where you've got generators on the edges and you've got states. And can you compare that to Cayley graphs and things?
Yes, you can. And in fact, while we were talking, I just found a PDF file for a talk that I recently gave at Santa Barbara on this very subject. So why don't I run us through
please,
some
go
material?
ahead.
Because you'll see how it touches precisely on the issues that you have raised. So this talk is actually already on the KITP website for anybody who wishes to indulge themselves. So let me just advance so I can get to the relevant stuff. Because normally when I talk about supersymmetry, I have to worry about the fact that most people don't know as much as you do about supersymmetry. So I have to actually explain supersymmetry first. And that's usually part of my talk. So we're going to skip all that stuff and get right to the meat of your question, which I just found. So I'm going to have to share screen to do this.
Go for it.
Can I do that?
Yep. Yeah, go for it.
Okay, here we go. Okay, so when I talk about the problems that I'm worried about, I like to use SU3 because that's something, like I said, you were working with it when I met you. Lots of physicists understand this, and it makes what I'm trying to do more concrete. So let's rapidly, for other people on this call, not for you, but for the benefit of other people on the video, let's go through the SU3 really quickly. So with SU3, like I said, I call it the golden gateway to understanding polytopes that undergird symmetry. So SU3, the way you learned it first, they tell you there's these 8 matrices that Murray Gell-Mann invented. Here are the 8 matrices. At the bottom of this, you find out there's a set of commutation relationships that say these things close. There's also this thing called the D coefficient, which only you and I would know about. But anyhow,
I remember those, yes.
I do too. And then for people, since I have to give this talk sometimes to people who don't really know a lot of linear algebra, I have to remind them of the definition of eigenvalues. That's this slide. And eigenvectors. And then here's this decomposition that you were talking about. We take all the generators of SU3, we break them up into 2 commuting ones, T3 and T8. T3 and then we find the eigenvalues of those generators. Here are the eigenvalues listed for T3. Here are the eigenvalues listed for T8. And then to get to representation space, these eigenvalues should be thought of as the coordinates of something. Mm-hmm. And so when you do that, you get to this funny kind of a lattice. And this is what I mean by the polytope. So the E1, E2, and E3 are the generators that don't commute. And in fact, we put them together into permission pairs. And when you look, if you take an eigenstate of T3 and T8 and apply one of these operators to it, if you start it at one point, these operators will move you to adjacent points. Mm-hmm. So those are the raising operators. The ones that act on the other side are the lowering operators. So you wind up with the idea that SU3 is actually related to this crystal that sits here. And representations are, in fact, collections of points that sit at the vertices of these crystals. So on the left side of this, we have one representation. And on the right side, we have a different representation. But for physicists, what we're looking at is exactly the weight space diagrams for quarks. So here's the up quark, the down quark, and the charm quark.
Right. This is strangeness and isospin.
Yeah, isospin, exactly. Isospin.
No, isospin is the F3. F8 is the...
Right. This is isospin in this direction. This is strangeness this direction. So as I said, they come about because these polytopes say that representations are actually collections of points at the vertices of this lattice. So, but here's another representation. In fact, this is like an octet representation with the proton neutron here, the lambda particle, the sigmas, and even the pions actually also sit in a different octet, but it's an octet. So the point is that we understand a lot about group theory because we understand the crystals that are defined by the eigenvalues of the commuting generators. This is a central part of understanding group theory. And so here's another, just to go this one more time, here's another representation, this is so-called decouplet. And in fact, this is the representation that Murray Gell-Mann used around 1958 or 59 at a meeting in CERN to tell particle physicists it's time to go learn group theory. Because up until that point, particle physicists did not study group theory a lot.
And that was where the omega minus comes. Yeah,
there you go. There's the omega minus. And so this is the level of understanding that I want to have. Well, look, if someone wants to give me this, I'll take it, but no one has actually done that. So if you have a question that no one knows how to answer, then it's your responsibility to try to answer that question. So I've been asking these questions for a long time, and like I said, no one seems to know the answers. So adinkras, I along with another physicist named Michael Fox, I concluded that adinkras were the way to try to solve this problem. And I'm coming to adinkras next. Here's a final.
Let me ask a question here.
Yeah.
Okay. I realize that this idea of the representations of SU3 just being filling out this kind of triangular lattice, I didn't know that idea, or at least I didn't remember that I knew that idea.
You probably knew it at some point.
Okay, but so my question would be, if you look at the other SUN groups.
Oh yes.
Does it work? Does
yes.
it go to higher dimensions and it
yes.
just works?
Yeah. So if you do, let's go back to SU2. The lattice for SU2 is just the real line basically, and the point and the vertex points are that's what we are integers and half integers, but that's what we do with spin. That's SU2. SU3 is this lattice I just showed you. SU4 is actually kind of a tetrahedron. So it has SU3 as its base, but then there's another, so in addition to T3, so for SU3, it's the isospin generator and the strangeness generator that are the commuting. If you do SU4, there's one more commuting generator. So the base, in fact, the way to think about SU4 is that the object I'm showing you here, think of this as a base of a tetrahedron that comes out of the paper, and that other direction is associated with that other commuting generator.
Which is basically charm. I mean, in the case of quarks, that would just be charm.
That's correct. That is correct. So yeah, so it turns out that this sort of crystalline structure is ubiquitous for all compact groups. And by the theorem that one of our colleagues put in the chat, it extends to some non-compact groups too. So my goal has been forever at some level to ask, where are these kinds of crystalline type structures associated with supersymmetry? What are they and where are they? So this is just another SU3 representation. Why is my machine not advancing? Hang on a second here. There we go. So the question is, can polytopes underline supersymmetry? And that's what I've been busy studying. So now I'm going to take you backwards to Salam and Strophe, because these are those things that you were talking about, anti-commuting coordinates and commuting coordinates. This is the idea of Salam and Strophe. And this object V, which is a function of these, is a superfield. And this is the type of thing that drew my attention as a graduate student, because I had never heard of this idea before. Now, the anti-commuting coordinates, there's an index that takes on 4 values. Why 4? Well, because these anti-commuting coordinates are also supposed to be spinor representations of the manifold that you're talking about. So if you're talking about space and time, the spinors that associate space and time are the spinors that you see in the Dirac equation. They're 4-component long objects. So if we were in 11 dimensions, for example, which is where I've been working recently, there would be 11 of these coordinates, 1 temporal and 10 spatial coordinates. The number of these is 32 because a spinor for 11-dimensional space has 32 independent components.
Mm-hmm.
So this is the basic idea of Salama-Strofty. And what's interesting, a couple of interesting things I should point out is that, so this object is actually a spinor in this expansion. This object is a spinor, but the other objects are bosons. And so this is how the superspace idea unifies bosons and fermions. Basically, the bosons are associated with one power, with say all even powers of this Grassmann coordinate, and fermions are associated with odd powers, or vice versa. It doesn't matter which way you do the mapping. But
so wait a second. What is this new object or this V object? What is this quantity that you're writing out here?
Say again.
What is that nu or V or whatever it is? That looks like an expansion around.
Yes, this is the superfield that I'm talking about.
But so what's the right-hand side is the decomposition of that?
Oh yeah, there's the decomposition of the superfield into ordinary space components. So V, this thing I call V sub B, that's like the photon.
Okay. But so wait a second. So this is just a mathematical identity, just writing out this thing, which is a big super vector, so to speak, written out in terms of sort of more conventional kinds of objects where your lowercase v's there depend only on the commuting space variables. Is that correct? And
that's correct.
So in other words, this is, but you could have also presumably written this out as an expansion where you have well, no, I see. You can, the maximum power of theta is 4 because
here. Yeah.
Is that right?
For 4 dimensions, yes.
Right. Okay. And then I see. And those C, alpha, beta, and so on. Those are simply some bilinear invariants that are associated with the space-time manifold that we're talking about. And the gamma 5 that's there, is that an ordinary gamma 5 or is that some
longer?
It
is. It's the gamma 5 that we use in weak interaction theory.
Oh, I see. But, okay, so this is the 4-dimensional version. If you were writing out the 11-dimensional version, this would be a much longer formula because you would have up to
it. In fact, by the end of this talk, I'm going to talk about the 11-dimensional version because last year, working with 2 of my graduate students, we became the first people in the world to actually know how to do the 11-dimensional expansion.
Oh, okay. Good stuff.
And it's based on using adinkuras, not on using superfields. A number of people have asked me, am I just rewriting things that people know? I wouldn't waste my time doing that. I want to get the things people don't know. And in fact, we now have this concrete proof that we can do things no one else can do because we use adinkuras.
Good. Okay, so now, sorry, I derailed you here. Keep going.
No, Stephen, I'm enjoying this.
Okay, so now how when you talk about, so now you're about to describe these adinkra nodes.
Yes, that's where I'm going next.
Okay.
Okay, so this gets us to the work around 1975 of Salama-Strofty. That's what this slide gets us. Mm-hmm. And it begins to introduce people to the notion of superfields. And the component fields, the things that are listed as component fields, are the fields that anyone who's learned quantum field theory would know about. So this thing you would associate, for example, with a photon. These are scalars and those are spinors. So in 11 dimensions.
When you say level there, is that the number of thetas that are appearing?
Yes.
Okay, that's not interpreted as, for example, spin. That's the number of thetas. What's the physical interpretation of that?
So the number of thetas actually do change the spin representations. So the idea is that theta, if you know something about young tableaus, that's the way to say it. Mm-hmm. If you ever use young tableaus, you should associate the thetas with a young tableau where the range of indices runs from 1 to 4.
Okay.
But young tableaus have a natural multiplication rule because if you take the product of 2 young tableaus, you get a different set of young tableaus. And in fact, that's the way to think about this second line here. If you think of this as a Young blow of, say, a single box, then this thing is box times box. And as you know, with Young blows, if you take box times box, there's this decomposition that you can write into irreducible representations. So box times box is equal box up, box horizontal, and this is the equivalent. It's a little bit more complicated, but same general idea.
Okay.
Okay, so I'm going to skip some of this 11-dimensional supergravity stuff for the moment. I'm going to fly through it because the central part of our talk discussion is centered on the representation theory. So let me fly through 11 dimensions for a moment. Back in the late 70s, middle to late 70s, this theory called 11-dimensional supergravity was discovered by Julia and Cosmere, two French physicists. And the component fields are what I've written here. One of the component fields is the graviton. So it's a symmetric second rank representation of the Lorentz group. They also have a 3-form. So those are the bosons. And then the only fermion in their theory is something that is called a gravitino. It has both a spinor index and a vector index. So these things, so let me back up a slide. These things I'm showing on this slide should fit inside of some 11-dimensional analog of this.
Mm-hmm.
But no one has ever, until last year, no one had ever found what that thing was. No one knew what this was for 11 dimensions.
Wow, okay. I kind of always assumed somehow that there was some, okay, great. So you figured it out. This is good.
Yeah, and part of the reason it's difficult is because there are 4 billion different degrees of freedom in this 11-dimensional object, whereas here there are only 8.
Let me see. The 4 billion is a 2 to the 32 or something, or what?
That's exactly right. The number of the number of degrees of freedom goes exactly as the number of indices as 2 to the range of indices on the thetas.
Okay, so that's the analog of the Dirac equation in your. It would be a. Is that correct?
Yes. Okay, and so like I said, last year, starting in 2019. I finally figured out how to use my Adinkra ideas to answer these questions, which were actually behind why I was doing this. As I said, for years, people have asked me, aren't you just rewriting superfields? And I would say no. But then they said, well, what's different about what you're doing? I'm like, I'll get back to you on that one. Now I can get back to them. So during 2019, 2020, working with 2 of my graduate students, we did the complete analysis based on Adinkras, and we now know the complete detailed decomposition of that V thing in 11 dimensions, and we can tell you where those component fields are. It turns out the graviton and the 3-form are at the 16th order in the expansions of theta, and that the gravitino is at the 17th order. And so it's, believe me, and why, it's a whole nother talk to explain to you why we know these things. Because we want to get.
That means there must be a gazillion other particles.
There are lots and lots of other particles in this thing.
Are there less than 1 billion particles? Or are there?
Yeah, well, the thing is, on shell, which means when the Dirac equation applies, when Einstein's equations apply, when the analog, so the equation for the 3, if you have a form, the equation of motion is always at the form d star d acting on the form, where d is the differential. And so there's a differential operator that acts on that 3-form by the same rule. That's on shell. That's when you apply the classical equations of motion. These billions of particles that you talk about are what we call auxiliary fields, Stephen. They do not propagate Cauchy data.
Okay.
They enter algebraically. You can think about them as Lagrange multipliers.
Why is that obvious from, I mean, so the decomposition of that thing you had, the V, why is it obvious that there are, okay, so you're saying certain excitations, I'm not understanding why there will be 2 kinds, why some things are like Lagrange multipliers and some things are actual degrees of freedom?
Because
is it easy to see why they're both things?
Yeah, no, you're asking the right question. And the answer is, it's not just a matter of writing those things. You have to write actions for them. It's the actions for these things that determine what's dynamical and what's not.
Okay, so in other words, then the action is determined by some symmetry consideration. What the possible actions are is determined by having this some kind of analog of rotational symmetry for the supermanifold.
That is correct.
Okay.
And
so
that's
you're saying if it is essentially rotationally symmetric in the supermanifold sense, then any such action will contain certain excitations which are like the graviton and so on, and other things which are merely essentially, I don't know what you call them, gauge degrees of freedom.
I would just say Lagrange multipliers. They're kind of like Lagrange multipliers, which are not.
Why do you call them that rather than, like, in a sense, gauge in the sense of general relativity, as in arbitrary extra data that is just undetermined by the equation of motion?
Look, perhaps I shouldn't call them Lagrange multipliers. We typically use the word auxiliary field in all supersymmetrical theories. When you do not apply the classical equation of motions, there are always these fields whose equations of motion say they're equal to zero. And that's what I meant by they don't propagate Cauchy data.
Right.
And so of these gazillion other fields, every single one of them is of that character.
Okay, so there are no new particles, basically.
Not for this.
Okay. So now I have two questions. First is, well, are you about to show the great Adinkra picture or something?
I was, but ask your question first.
Well, no, I wanted to see the picture, but then I was going to ask the why are they called Adinkras, but maybe you should show the picture because that may explain the answer to the why they called Adinkras.
I'm not sure that's going to explain it, but the picture I'm going to show them is it's a joke my son did. I tell people if you're going to be calculating something with billions of degrees of freedom, you better get a computer to help you. So my son made this up for me.
I like that very much. Yes. That's how we like our people using our technology. We like them to feel that way.
And believe me, it's like putting on the Iron Man suit, except for mathematics. And so that's how I'm able to get these answers that no one else has gotten before, is because we know how to combine sort of the analytical thinking that we do in here with the design of algorithms that will give us answers. And we're the first people to actually be able to do this. So
I have the impression in the world of like tensor manipulation and so on, that there've been, back when I was doing, tensor stuff back in the late 70s, there was all this question about how you would multiply tensors together and find canonical forms of the products and things. And I always thought that there must be some graph theoretic way to do that.
Yes,
and I think in fact Penrose had invented such things years earlier, but I didn't know that. But it seemed like it took another 25 years before people really streamlined, just in terms of ordinary tensor, tensor multiplications and so on, the kind of graph theory meets tensors. But they seem to be they're a natural, graph theory and tensors seem like they're a natural match.
Yes. I mean, that's where our research has pounded into our heads, because in dealing with these billions of degrees of freedom, if you're going to actually try to write tensors, it's almost impossible to figure out, how do I construct code that will do this? Whereas if you start with a graph, which is very visual, and with the nodes having well-defined properties, like I said, essentially what you do is you take the nodes to be Young-to-Blows. Well, there's this thing called Climax Formula, which is a general formula for multiplying Young-to-Blows for arbitrary groups. You just code this up. Look, our codes run on laptops using Mathematica. But you have to have the insight to understand what things. Let me put it this way. For years, I know people who have tried to take this expression and write it in terms of code so that they could get computer programs to calculate these things. Good luck with that program is all I got to say. The way we got around it is because we didn't actually write code to describe this thing. We wrote code to describe Adinkras, and Adinkras, as we'll come to, are graphs.
So, in some sense, what you're saying is, beneath what looked like algebraic mathematics, there's a discrete mathematics kind of framework and foundation that's a much more efficient way to handle the kinds of things that are going on. That even though this looks like it's continuous mathematics and you're taking polynomials and things like that, that actually the true structure is given by some discrete mathematical object. Is that a fair way to characterize it?
You know, Stephen, I once met this guy named Stephen Wolfram who told me this years ago, and I didn't believe him.
Fair enough.
Okay, but it's true. I mean, I know it's self-discovery. We found out that yes, like I said, anybody who wants to try to put this on the computer, good luck with that, because it's not going to happen. Whereas it's very strange. Once you understand this in terms of graphs and discrete mathematics, it becomes conceptually beautifully simpler.
Okay, let's see how it works.
Okay, so here we go. Okay, so this is just summarizing our results. We did the decomposition. It turns out that there are 1,000 fields. So I talked about degrees of freedom a moment ago. I said there's over 4 billion degrees of freedom. But the number of fields is less because, for example, the photon is 2 degrees of freedom, right? So a field can have more degrees of freedom than a counting. It turns out that there's just over 1,000 fields inside of that 11-dimensional analog. And like I said, we're the first people to be able to tell you exactly what those fields are.
What is that spin 3 thing or whatever it is, the A mu nu rho? What is that?
The 3 form.
What is it?
It's so in Cosmere and Julia's theory of, well, let me say it this way. One of the hallmarks of supersymmetry is that the number of degrees of freedom have to be equal. And so if the theory just consisted of the 11-dimensional graviton and the 11-dimensional gravitino, you will never get equality of degrees of freedom. And so there's a condition of equality of degrees of freedom that says you must introduce this 3 form in addition to the graviton.
But that's a spin 3 massless field or what?
Well, remember we're in 11 dimensions now, so you have to be careful about your language. But yeah, I'd say it's a 3 form. I can, if you want to know degrees of freedom, I can pull up another talk because I get
okay. You're right. I'm being silly here because I'm not remembering that this is in 11 dimensions. So the decomposition down to a spin as a creature of
the dimension that you're in,
of SO3, so to speak.
That's right, exactly. So anyhow, so now I'm going to take you to Adinkras and how we get to the representation theory. This started with a physicist named Michael Fox. My work with him in 2004, and I was in I was in the country of Georgia in 2004 visiting. And one day I looked at the archive and I saw a paper by Michael Fox and one of his collaborators. And it looked strangely like one of my papers, I mean the contents. And so I sent him a message saying, are you aware of the research I've done? And I was already doing Adinkras. Well, I was already studying the adjacency matrices to Adinkras, not Adinkras themselves. Because as you know, graphs have adjacency matrices. And so Michael and I started talking. And after about 5 or 6 weeks, we had this paper that's described at the archive. And the basic idea is, if you start with supersymmetry, like say 11-dimensional supergravity, we say under some kind of projection, there must be something that retains information. And here, this is the, we say, think about it as the sun shining on a pyramid. The pyramid casts a shadow. The shadow carries some information about the apex of the pyramid. So how do you actually implement this strategy? Well, what we did is say, okay, well, fine, let's use Einstein's light cone. Normally, an observer, you can put an observer at the origin. And the goal of field theory is that you state some initial set of conditions on fields, and then you predict in the forward light cone what are the configurations of those fields. This is a problem that we'd like to be able to solve generally for supersymmetry. No one knows how to do that. So we said, well, let's solve this simpler problem. Let's just look at saying we have a bunch of fields and we put initial data on them. And then we ask, how do they propagate along a single line into the future light cone? And so effectively, that allows us to turn field theories into, all fields become a function of a single variable. And that single variable is a time-like variable, because if you're in the forward light cone, you can always pick a Lorentz transformation to make this the time axis.
So wait a minute. So what you're saying is, instead of looking at full spatial dependence, you're saying just look at one point in space and look at what happens at one point in space. Is that a way to think about what you're saying?
That's one way to think about it.
Okay.
And so if you implement that, as I said, fields become functions of a single variable we call tau. Mm-hmm. What's really interesting is things like spinors, which carry indices, continue to carry those indices. And so the question is, you have to figure out what the groups are that they're talking about. And so that thing that I showed you, that V thing that I showed you, if you use this reduction that I talked about, it turns into this graph.
Okay. What are the numbers there?
Let's go back to the V object. They're the same numbers you saw here.
What? Okay, so that 4 thing, that's the size of the spinor representation. What when you?
It's not a spinor. It's actually a boson, and that it's a Lorentz vector.
Okay. But the other 4s above it, those are that's
right. And you put yourself when we talk about this in terms of Dinkin labels, we use red boxes for spinors and blue boxes for bosons.
Okay.
So you have to build your code so that it knows the difference. Yeah, you're right. You have to put some kind of indicator, and so we do it with color when we explain it to people.
Okay.
Okay.
All right. So that's the 4-dimensional case you're about.
Yes.
You're showing.
Yes. And so we discovered that these things have bits naturally built into them, because it turns out that these graphs always contain four-sided polytopes, one-dimensional polytopes. That is, squares are always inside of these things, it turns out. And if you start with something that is square or a cube or a generalization, then you can always, and by the way, it's only the topology of these objects that matter, not the actual geometrical shape. So if you treat hypercubes only with respect to their topology, the only thing you really care about are the vertices, and the vertices on a hypercube can always be labeled by this set of numbers.
Right.
And plus and minus 1 is always, +1 is -1 to the 0 power, and -1 is -1 to 0 power. So actually, bits specify the vertices.
Okay. Okay. You have, okay, so that's a bigger one. Okay, fine.
And so here is the full.
So this is a hypercube. Basically, you're saying there's a hypercube.
Right. This thing is actually, the thing I'm showing you is a hypercube in 4 dimensions.
Right. So it's a what you know, to a Boolean hypercube would be kind of
Boolean hypercube, absolutely.
Okay. All right. And so each, I see. So that algebraic expression, you can represent that by just saying there are these different kinds of things, and you can say based on whether there's a 0 or 1 in that position, what that monomial looks like.
That's correct. That is correct.
Okay. And the colors correspond to which kind of operator you use.
So remember I said we do this reduction. So there are operators in 4 dimensions that act on the fields, and they carry all kinds of indices. Among the types of indices they carry is an index for them that's equivalent to the, if you give me a spinor, it actually is a description of 4 functions. So you can think of that index as denoting which of those 4 functions a spinor constitutes.
Mm-hmm.
And those indices, if you want to illustrate them in the graph, you might want to choose colors for different values of them. And that's the colors that you see in this diagram. Okay. So the information about the spin is actually, a spinor in this language is a collection of these links. It's not a single link.
Okay. Okay. So you could in fact have drawn, in terms of a graph, you know, you could have drawn that as a graph with multiple edges there.
Yes.
Might be a good thing to do. I don't know.
Well, maybe we haven't got. So it turns out, let me skip the story about error correcting codes, because it turns out this is what I told you when the first time I was telling you about adinkras, is that we find out that the irreducible representations are actually governed by classical error correcting codes.
Which ones? Which codes?
Classical error correcting codes.
But which ones? Like Golay codes or something?
No, they're what some people call the expression is self-dual error correcting code.
Okay.
Error correcting codes. I'd have to look it up, Stephen.
Okay. Okay.
But the point is that error correcting codes actually control the irreducible representation space, which was a shocking discovery for us, but it turns out to be true. So now you asked me about the name. So let me tell you about the name. So
wait a
Michael,
minute. I'm still looping. Hold on. I'm still looping on your polytope. So the thing starts life always as a Boolean hypercube.
that's correct.
And that Boolean hypercube is then positioned in space where essentially there are bosonic and fermionic degrees of freedom at different layers in this Boolean hypercube. Is that
That is
right?
correct.
Okay. And then and the thing that you're saying in terms of the way that you construct the representations from this and your thing that was, you're saying there's some equivalence classes in this Boolean hypercube, and that's
That is
what
also
corresponds.
correct.
Okay. So the representations are some kind of classification of the equivalence classes or something of what?
Yes, that is also correct.
Okay.
That's the problems that we're working on these days. Let me keep going.
That's
I love, look, Stephen, I love talking to you because you catch on to these things very fast, as opposed to me having to explain over and over again, which I often find myself doing when I'm trying to tell people what it is that I'm doing.
Fair enough. Okay, so now the Adinkra word, the Adinkra name.
Yeah. Okay. So the first time so as I said, I was initially studying the adjacency matrices, because if you have a graph, there's a well-defined notion of an adjacency matrix. And in 2004, I had been sort of studying the adjacent. Let me go back and give one other person credit. The whole reason I started studying the adjacency matrix is because of one of my students, a young woman by the name of Lubna Rana. She was one of my PhD students at Maryland. I gave her a toy problem and she came back and I saw these matrices and I kept seeing, I gave lots of problems and I'm like, there's something interesting about these matrices. That's how I started studying the adjacency graphs. In 2004, by my conversations with Michael, we went from the adjacency matrix to the full graphs. And this started with an email conversation when I was in the country of Georgia. About 6 weeks later, we had written a paper by sending questions back and forth and recording the answers. And we had this paper, and by the time we ended it, I was actually in West Africa. I'd come to the United States and gone back to international travel. So I was in the West African country of Mali. And so Michael, who's a European American, he was actually in the Czech Republic the entire time we were exchanging email. But he had been to Africa at least a decade before I had ever stepped onto the continent. And so we both figured that these graphs were going to lead to something very interesting. And so, Michael, in our business, if you find a piece of math that you think is going to lead to something, you give it a name. And so we had some discussions about the names. And then Michael, as I said, who was much more knowledgeable about West Africa than I was, said, we can name them Adinkras. And I'm like, what is that, Michael? And so he introduced me to the traditional Adinkras in West African culture. This is, by the way, a traditional Adinkra that my cursor is circling around. This is the cover of Physics World edition that came out in 2010. We were the cover story.
So what language was the word Adinkra originally from?
It comes from, hang on a second. The word is Swahili. It's in Swahili.
So do you know how to say it in the native kind of pronunciation?
No.
Okay. Anybody on this call know that?
Stephen, I tell you, Steve, I tell people, I have acted in typical colonial fashion. I've simply taken the name.
Hey, Tally, if you're on here, do you happen to know how to say it
I do not, sorry.
Okay. Oh, well, thought you might. Okay. I would have thought, Jim, at some point in your travels, somebody would have said, no, just like Murray Gell-Mann always used to say about almost every word. It's really pronounced whatever.
Yeah, that's a very interesting analogy because Murray certainly was good at that.
Okay, that's so I know another trivia question. So how many countries have you been to? Mali is not a country that not one of the common physicist countries.
Yeah. In Africa, I've not been to very many countries. I've been to Mali, I've been to Benin, I've been to South Africa, I've been to Morocco, and I've also been to Senegal and one other country whose name I can't think right now. So it's less than 10.
So what has taken you to all these different countries?
People invite me, Stephen. They simply invite me.
Fair enough. But so you, I mean, to segue a little bit, and there's more physics to talk about, but I'm curious to talk a little bit about.
Okay, let's stop the physics. I'm having my fun. This is my playground.
It's actually, I see all kinds of comments on our chat here, because there are at least two groups of people here who I think have things to say that are actually pretty closely connected to the whole Adinkra story. And in fact, Tully is commenting here that this thing he's been studying about quiver geometry, which is deeply related to the things we're studying, looks like it may be closely related to Adinkra. So I think this looks like a rather interesting conversation that is probably going to take us into a pretty technical direction if we do it right this moment.
Yeah.
So
let me let's do the chats for a bit, because there's a comment in the chat from David Chester. He says there's supersymmetry beyond d equal 11, and he's of course right, because one way once you start thinking about supersymmetry in terms of these Boolean cubes, since we know that hypercubes are among the small number of higher dimensional objects that go on forever, then yes, that means supersymmetry will go on forever. So David's comment was exactly right.
So what does that mean? Does that mean that there exist sort of, what does that mean for string theory, for example?
I don't know, because as you well know, Stephen, in string theory, there's the notion of critical dimension, but that is a requirement of quantum order.
Right.
And so far in our discussion, we have said nothing about the quantum behavior of these objects.
Right.
Well, if you look at bosonic string theory, it comes in 26 dimensions, but there's actually fermions that you can find at that level. There's some new mathematics that I published some work on, and you can actually find some superalgebras up in like 30 and 32 dimensions that lead to a world volume in like 11 dimensions, for instance. So, and it looks like the lower world volume has the standard model, and then you can get higher matter multiplets. Maybe they're related to dark matter or something like that.
Yeah, well, as I said, once you understand that the origin of supersymmetry actually is these Boolean hypercubes, then it's obvious that supersymmetry is far broader than most physicists have studied it, and I simply haven't looked there. By the way, David, are you the Chester that spent some time at Princeton or working with people at Princeton?
No.
Okay. So anyhow, what else do you want to do while we're?
I was thinking. I mean, by the way, your description of Adinkras and the way that they come from supermanifolds is okay. But my last technical physics comment, perhaps, is in our models of space-time and so on, involving these hypergraphs and so on. One of the things of considerable interest to us, which we have not figured out properly yet, is what is the analog of the rotation group in one of these growing hypergraphs?
Yeah.
Because if we have, and then the question is sort of what's the analog of, in these hypergraphs, we don't necessarily have integer dimensional space-time. And so we have this problem of what is the analog of, the whole theory of Lie groups and all these kinds of things.
Sure.
When you're not in integer dimensional space.
So, Stephen, you and I have both said that we may be approaching the same problem from two different ends. So let me tell you how I see the emergence of space-time symmetries. Because the important thing in the way that I do this is to ask, so there's several different ways you can say it. So I have a bunch of mathematical collaborators that I've been working with for over a decade. And so they sort of keep me mathematically pure. And so the way that we often approach the problem is say, okay, what is the absolute minimum data that you need to start to build Adinkras? And the minimum data, as you identify, is Boolean hypercubes. Now, these colors, as you pointed out, we call these decorations. These are added, you can think of these as sort of added quantum number that the links can have. The nodes can also carry extra information other than just saying that there's a single function there. And in our work where we solved the problem on 11-dimensional supergravity, the nodes are actually Dynkin labels themselves.
Okay.
So the Adinkras I'm showing you now are the simplest possible Adinkras that we've used to explore the ideas about the mathematics that underlies this approach to understanding the symmetry. But if you actually want to do physics, what we will tell you is you start with the Adinkras, where the nodes are actually themselves Dinkin labels. There are rules about what Dinkin labels can be associated at different heights of the Boolean hypercube. We know what those rules are. They're actually in the paper on 11-dimensional supergravity. And so that's the extra information. But we have to put that in by hand, Stephen. It doesn't naturally come to us from any place. We put it in by hand, and that's how we're able to answer these questions.
So, I mean, the exercise, I suppose, for us might be, if in D dimensions for integer D, you have a Boolean hypercube, what would you have? What is the thing which in integer dimensions is a Boolean hypercube? What is that? How does that interpolate in fractional dimensions? And my guess is that the answer is in, when you're assembling the Boolean hypercube, sort of when you've got all the pieces there, it can be an integer dimensional Boolean hypercube. But when you kind of shatter that graph and have it not be something that has, has all the pieces there, that's the kind of thing you will see in intermediate dimensions, I would guess.
I would also agree with that. That's the most likely thing to happen, is that there's some kind of an obstruction. Something you can think is you can call it an anomaly or a consistency condition, but there's some kind of obstruction in in what you're doing that will tell you that among the general class of objects that you can construct, if you want something like Lorentz symmetry to emerge, this obstruction will have to be satisfied.
Right. Well, right. But you see, I think the thing that's different in what we're doing is in our sort of building up of space-time, we have very large hypergraphs. I mean, you're dealing with, in your thing where you're dealing with the representation theory, I would suspect, okay, wild speculation, okay, that the thing you have is like a representation of something like a Lie algebra. And,
something like that.
Right, and that in a sense, what we're saying is we're going to look at the whole group, and you might be able to represent that, you might be able to think of that as something where there's just this little tiny Lie algebra piece, which then gets just copied and copied and copied. Right. But in fact, in our setting, when, for example, you're not in interdimensional space, the picture is not really quite that it's this kind of homogeneous thing. We just have copies of the Lie algebra, but rather something where you have an approximation to something that can be represented using the algebra that comes from having this big hypergraph.
Sure, and that idea doesn't surprise me. There's something else I haven't told you about Adinkras. Adinkras, in their full realization, are actually Verma modules. These nodes that I draw are actually, there's sort of infinite numbers of copies of them. So these are actually infinite dimensional groups. We're aware of that. We haven't talked about it in any of our published work, but certainly in our private conversations with our mathematical colleagues and that I've been collaborating with, this is something we've said from the very beginning. We're just not ready to explore the implications of that.
Wait a minute, what's infinite dimensional? So you mean that this diagram, this Boolean hypercube, is somehow infinitely copied?
Yes.
Oh, nice. Okay, that's very similar to what I was thinking. Yeah, because I mean then what I was, the speculation would be for something which is a genuine sort of closing Lie group-like thing, then you've just got copies. But for something which is more messy, of the kind that our hypergraphs are, it's not pure copies. It'll be something where on some statistical average, it will look that way, but not on a microscopic scale.
So there is an infinite Lie algebra that we've never, like I said, we've never really talked about it in our publications, except for one publication, but we're well aware of its existence. Okay. And in fact, right now we're using this idea to look for quantum error correcting codes, because I and my colleagues, we just like to explore this mathematical space and see what's there.
Right. So I mean, I was going to sort of zoom out a bit and talk about kind of the world of physics and so on. And I know you.
Well, let's do that.
You've been involved in lots of things that I find, like the government advisory committees, and now you're now actually president of the American Physical Society, or are you about to be, or about what's the?
Well, I can tell you, Stephen. Your question as well. I wake up every morning and ask myself that same question: Am I really the president of the American Physical Society? And the answer turns out to be yes, because every day is destroyed by some obligation.
Okay.
I tell people I get very little chance to do physics this year. I mean, it's just been. For example, yesterday part of the day was spent talking to some officials at the Department of Justice. We have a meeting with we're supposed to have a meeting on tap with the presidential science advisor in the next couple of weeks. Where I mean, the range of issues that I thought this was going to be just an honorary position. I found out it's not. So, yeah, Stephen, I do a lot of stuff. I mean,
yeah. We might want to stop sharing the screen because that way we get a bigger.
Okay, let's do that.
There.
So, you know, I actually am the only physicist I know who's had writings cited by the U.S. Supreme Court. So, yeah, for me, I love doing physics.
What were those about? Wait a minute! Don't tell me Adinkras are in the record of the Supreme
No, not Adinkras. It's. Remember, I told you that Salam started me thinking about diversity back in the 80s.
Uh-huh.
Well, I've been writing not a lot of writings, but a few essays. Less than a dozen, actually less than half a dozen. But one of those essays wound up being cited by the Supreme Court. So I do that.
In what decision? In which decision?
The decision about, it's called Fisher versus Texas. It's about admissions.
Oh, yeah, I remember that case. Yes.
Yeah. And if you remember, something really weird happened. The Chief Justice, during the presentations that the lawyers for both sides were making, the Chief Justice asked the following, to me, very strange question. What value does a minority student bring to a physics class? Okay. Which is an extraordinarily odd question, because he could have said to a class, he could have said to a science class, but he said to a physics class. This suggested to me that he might have actually, well, more likely one of his interns, probably read an essay I wrote, and it's probably the essay that was cited in the final decision for the case.
Huh, very interesting. Because that particular student was not a physics student or anything.
No. That's why it was weird that he should ask this question. She was not a physics student. She was just a student trying to get into college, and her grades weren't in the top 10 of her high school, top 10% of her high school.
Right. But so I mean, actually, with the American Physical Society, how much has that gotten involved at this point with kind of political type? I mean, I thought it was just a thing that published Physics Today. That was the only time to put on conferences.
First of all, Stephen, you made a comment now that a lot of people think. The American Physical Society doesn't actually publish Physics Today. Physics Today is actually published by the American Institute of Physics.
Oh, yeah. I did figure that out. Yes.
It's a totally different entity.
Wait a minute. Is it totally different?
Yeah, it's a totally different. It's a totally separate, different organization.
But so why do members of the American Physical Society, which I've been a card-carrying member since like 1976 or something, why did they get copies of Physics Today then?
Because it's a benefit of being a member. Even though American Physical Society doesn't publish the journal, it's a member benefit.
Okay, but like Physical Review, is that published by the American Physical Society?
Physical Review and there's a whole series of physics reviews, Physical Review, those are published by the American Physical Society.
And is that the main financial driver for the American Physical Society?
It is indeed, Stephen, it is indeed.
And so then, okay, so what else does the American Physical Society do?
So what else does the American Physical Society do? Well, it turns out we're in constant conversation with government, which is, I kind of knew this, but I didn't know the extent. So I mentioned a meeting with some individuals at the Department of Justice earlier this week. Early on in my presidency, I was asked to represent physicists in front of Congress and talking about some of the things that physics does when we were looking at appropriations to support research at universities, because the National Science Foundation and Department of Energy, all those places get their money from Congress. And so somebody's got to actually be talking to Congress to convince them that their money is well spent. So that's something that falls on the American Physical Society to do in our discipline. And as I said, I did that earlier.
So what is your pitch for physics these days?
So what we did in the presentation, which was in February, we talked about the excitement around quantum computing, because that's something that, corporations are chasing that one. We also talked about some of the opportunities in fundamental physics, namely, so we found the Higgs boson, but hey, what else is there, right? I mean, so you try to give, now remember, there's only one physicist in Congress. So you have to give them some reason for wanting to support.
Is that the guy from Fermilab? Did he get into Congress?
Bill Foster's the name of the guy.
Yeah, I think he's a Fermilab related person.
So he's the guy. There used to be another physicist by the name of, oh my goodness, I can see his face, but I can't think of his name. There used to be two physicists in Congress, but there's only one right now. And so all of that falls on responsibilities of the APS. We also host annual meetings. And
yes.
So, there's the March meeting, there's the April meeting, there are fall meetings. We interface with physics organizations around the world. So I've met my counterparts from the European Physical Society, from the Japanese Physical Society. I have to give a talk to the Polish Physical Society sometime in the next 2 weeks. And so all of this liaison work to support the field of physics falls on the APS.
So I'm curious, though, to come back to this question about support for basic science by something like the US government. And I'm curious in terms of, I run into people who ask me, why should government support basic science?
The answer is very simple. If the government doesn't, it won't be supported. And if you think that we're going to be safer in a world where other countries support basic science and we don't, you probably got another thing coming.
Well, but that's an interesting point, because the country-specific support of basic science. I mean, I remember once asking visiting the NSF and asking a bunch of their associate directors, why do we support basic science? And they had kind of two hypotheses. One was, I suggested two hypotheses. One hypothesis was, to make American science, preeminent in the world. And the other was, there's a bunch of people who vote for, politicians, and, it's kind of like this is a way of paying back something to those people. And it was like, which of these is it really?
Yeah.
And they were very confused. And I because they didn't want to say it was a nationalistic type purpose. But that one makes sense at some level.
That does make sense to people in Congress, quite frankly, because they're, you don't have many science fans in Congress. Even people who are friends of scientific disciplines, if you look closely enough, in my opinion, you find that there are other agendas at work also. By the way, the other physicist was a guy named Rush Holt, who was at Fermilab. I'm not sure Bill Foster is, but Rush Holt.
Okay, but he's in Illinois, isn't he? Isn't Bill Foster in Illinois?
He may be. In fact, he may be Rush's successor. I don't know.
Okay, all right. We don't know. I just I remember seeing a bunch of stuff about him, and
you're right. Bill Foster is in Congress.
But so, I mean, just coming back to this question of kind of what, some people argue for basic science on the basis of, it's the thing that's going to trickle down to give us great new technology.
Correct.
Some people argue it's a kind of human resource development type thing.
Yes.
Some people argue it's kind of a hedge against sort of bad things that could happen in the world, and make sure what's going on ahead of everybody else. I'm just sort of curious what you see as being the.
I think all of those are true things. Every single one of those reasons, I think, is why this country supports basic science. But one has to be in my mind, needs to be very clear on this. The United States didn't support basic science to a large degree before World War II. It did afterwards. What happened?
Right.
Atomic bomb, right?
Right.
Let's be very clear on this, that this country, and probably most countries, support basic science because they recognize that if you don't, there's a danger that someone who doesn't like you will find something that will put them in a preeminent position of power.
Right.
Now, that's not why I do science, nor you. I mean, for me, science is, first of all, something deeply personal. My story in science began when I was 4 years old. I wanted to become a scientist when I was 4 years old because I saw a movie about scientists and space travel, and I thought, God, what I wouldn't have used the words, but I thought, what a great way to live a life. In 4 months, I'll be 71 years old, and it has been a great way to live a life, right? So, but the other idea is that maybe something that I do or you do, or certainly, well, you've already done this by the creation of Mathematica, but for me, it's always the idea that maybe some one of the mathematical widgets I find will prove to be extraordinarily useful in the future for our species. And the other thing is, so few humans actually do this. I tell people that science is humanity's survival instinct, because if things get terrible like climate change, or if we could, if we saw an asteroid coming towards us, how are we going to defend ourselves? It's going to be our technology. From where do we get our technology? It comes from our science. So science is actually humanity's survival instinct, is the way I've described it to people.
Yeah, it's a shame that in this time of the pandemic, it's a shame that science has gotten a bit derailed, I'm afraid.
Yes. Yes.
It's not, and the physicists have not been much involved, I think. There've been some physicists doing epidemiology kinds of things.
Right.
But I was recently looking, I had been at immunology, which I had looked at like 30 years ago. And I knew it had got to a certain stage, and I'm like, I wonder what's known now, and I wonder whether there are good theoretical models now.
Right.
And the answer is no.
Yes.
They haven't changed.
Right.
And there's a ton more detailed experimental phenomenological information, but it seems like the kind of thing. So I'm curious. When you look at the sort of flow of physics in the US and so on, and people doing these different areas where there's enthusiasm, like the quantum computing enthusiasm, which I actually am not a huge, I'm not hugely aligned with that.
Well, I'm not surprised to hear that, Stephen. And I like it. So look, don't repeat this. None of you, I'm looking at some of your faces on the screen. Like,
this is being live streamed, Jim. So whatever you say is out there in the world.
But the point I was going to make is that one needs to be extraordinarily careful in predicting the benefits that will flow from an advance in science. So yes, potentially, all the things that you hear about quantum computing and quantum information, quantum is the new buzzword out there. People in Congress know the word quantum. But as to whether those benefits will actually occur, we need to be extraordinarily prudent and not get our heads over our skis so that we are viewed as having failed to deliver something we said we would.
So in the quantum case, just for your, I think I understand this one reasonably well. I think there are two ends to that story that are both good, and there's a piece in the middle that isn't good. The two ends that are good, one end that's good is using physical processes, including quantum-related processes, to do computation.
Right.
That's perfectly sensible. We need something beyond semiconductors.
Yep.
The other end is the formalism of quantum mechanics, and the things that you can do. And I just wrote this thing about what I'm calling multi-computation, which is something that comes out of our models that is sort of in a sense, it's a version of a quantum-inspired formalism that I think is extremely powerful, and that's all good. But many things you can do with multi-computation, it doesn't have anything to do with the true quantum mechanics. It's just the formalism stripped away from the actual quantum mechanics. When you go in the middle and you say, can we do magic stuff using quantum mechanics and computation? Right. I think the answer is going to be no. I've thought the answer was no ever since like 1981 when I first started looking at this. I think that but it's a funny situation because the two ends are both very good. Yes. The middle, we just were looking at, there are like 60 quantum computing companies out there, and I could tell you all kinds of things about them.
Yep.
But I'm curious. Remember nanotechnology?
Yeah. Yes, we remember nanotechnology.
And remember that there was also so to me, nanotechnology was in many ways a tragedy, because there were a bunch of really pretty good ideas. All these things about molecular machines, molecular scale manufacturing, all this kind of stuff. These were good ideas, and they should have been pursued. but that was something which rode itself up. And I remember there was a big allocation of money in the US for nanotechnology, and there was a lot of rhetoric about nanotechnology.
Yep.
And it crashed. And I don't know. I mean, I'm just sort of curious because I'm.
Well, Stephen, let me give you a little bit of pushback on that. It has temporarily crashed, is the way that I would say it.
Well, I agree with you. No.
Okay.
No. It's a good idea. It's going to be back.
Yeah, exactly. It's going to be back. That's my point.
Right. But I mean, the question is, I'm just sort of curious in terms of understanding sort of the process of science interacting with the government. And we see things like, for example, okay, so, Manhattan Project happens, everybody, the government says this is really important stuff. Particle physics gets launched for a couple of generations, basically. Particle physics is funded as sort of a thank you for the Manhattan Project, is the way I see it.
I would not disagree with that characterization. Keep going.
Right, but so then, at some point that kind of runs out of steam. Sometime in the 1990s-ish or so.
There was a marker for that, Stephen. It was called the superconducting supercollider.
Yes. So what was your analysis? I remember, I happened to be at a dinner with Leon Lederman, actually, the day before some big sort of vote about the supercollider. And I spent the whole dinner trying to get Leon to think about one thing, which was, if the thing gets killed, what are you going to say?
Right.
Because people might remember what you say.
Yeah, and I assume you're talking about Leon Lederman.
Yes. I failed to convince him to think of something really good to say. But what should have, why did that happen? And what should what's your analysis of kind of what the story was?
Okay, so this, for the young people on this call, this is around 1991 or so. That was the first time I was on Capitol Hill, because there was an activity organized where a substantial number of physicists were organized to go to Congress and speak to their representatives about funding the SSC.
Mm-hmm.
And so, since the University of Maryland is actually one of the suburbs of Washington, D.C., and since even then I was interested in the welfare of our subdisciplines of particle physics and physics in general, I was one of those physicists. Okay. Now, my hair was long and black in those days, so I tell people, I should show you folks some of my pictures of me younger. But anyhow, I remember going, but since I was a relatively junior member of our delegation from the University of Maryland, Jogesh Pati was our most well-regarded and most well-known physicist. So I remember going with him and a couple of other people to speak to our Maryland representatives. And what I saw was appalling, quite frankly. He essentially tried to explain spontaneous symmetry breaking and the Higgs boson to a congressman. You can get some idea about how successful that was. And I was appalled, and I don't know how many times this was repeated with other groups of physicists going to speak to the congressman. But what I saw was that our senior colleagues had no real understanding that if you're going to talk to a policymaker, someone who is going to make a decision about, should I put in a new sewer system in my hometown, or should I send these folks money so they can search for this thing called the Higgs boson? It was completely clear to me that lots and lots of senior physicists did not have an understanding that would make them effective to convince people on the Hill to support the SSC. So after that day, I was up until that day, Stephen, I was very optimistic. After that day, I was extraordinarily pessimistic. I'm like, these guys don't know what they're doing.
Because they had no idea what was important to policymakers.
Well, they had no idea of the audience. And this is something that physicists often make a mistake about. You mentioned that I do lots of things, and that's true. But one of the things I learned very early in my career is that when you're going to give a talk, the first question you should ask is, who's my audience, not what I'm going to say. Because if you're not asking the question about who the audience is, you're likely to say something the audience will not either understand or appreciate. So this is something that has been, that we, physicists as a community, we've been very slow to learn this lesson. And we're still not really good at this. And one of the things that when I got elected president for the APS, this was one of the things I said in my candidate statement I wanted to work on. Well, little did I know that President Trump would be in office and that COVID would be in office and there would be Black Lives Matter. And so this is one thing that I totally failed at as president of APS, having an opportunity to work on this issue of getting our community to take even the basic steps of learning to be effective communicators. Now, in your realm, Stephen, you've had to do this because you built a corporation, and you don't do that if you're not able to talk to people. And so that was my fervent hope. Like I said, go back and look at my candidate statement. You see, that's item number one. I've not had a chance to do anything on that work since I've been president.
But so what do you think? I mean, in terms of, for the U.S. government, or for the people of the U.S., your argument. I mean, how would you explain? Let's say there's a question: should the U.S. build another particle accelerator? How would you answer that? Well, do you think the U.S. should build another particle accelerator?
I do, but the question is when, Stephen. Mm-hmm. So in 2006, I wrote an essay called "Is String Theory Phenomenologically Viable?" And this essay, I started the essay off by saying that we're about to go into an era where there will be data for particle physics, and that a lot of ideas I did not expect to pass muster. And so so that's why this strange title is. So the question was string theory going to survive or not? Mm-hmm. And one of the things that at the time, if you go back and look at the literature, enormous numbers of physicists were saying, yes, we've got to build the SSC so we can find the Higgs boson. And then we're going to find supersymmetry. Well, folks, we know how that worked out.
Right.
We did find the Higgs boson. And the LHC, when it was built, found the Higgs boson. And had the SSC been built, it would have found the Higgs boson faster because it was a much more capable machine. Mm-hmm. But the the LHC, has not found supersymmetry. Right. So in my 2006 article, I explicitly said, I don't expect the LHC to find supersymmetry. That put me in an extraordinarily small minority of physicists. In fact, so much so that most of you don't know about this essay, but you can go look for it and see that I said it. So what I claimed was the road to discovering supersymmetry is precision. That what you ought to be thinking about is building machines, but where the
luminosity or something is high.
Say again?
High luminosity rather than high energy.
Thank you. That's the word I was looking for. That would be the way to discover supersymmetry. And this is explicitly said in the article. Now, I didn't mention G-2, which looking back on it, I thought, well, how in the world did I not say G-2? Because it's also one of these high precision things. But I said the way to discover supersymmetry is to go for precision measurement. And then when you have enough confidence that you're seeing an anomaly, then you start thinking about building a machine to go after something like supersymmetry. Like I said this in 2006. I said the same thing in 2012, and I still believe it to this day. And so I was extraordinarily gratified this year when the results on muon G-2 started coming out. That looks like there's a real anomaly there.
Yeah, I wouldn't count on that yet. But
I'm not counting on it yet, but Stephen, I have my hope and dream has not been crushed so far.
Fair enough. But
right?
Historically, for example, charm quarks.
Yeah.
That was one where there was a little bit of indication from that, something was there, but
right.
It wasn't kind of a slam dunk thing. Now, the Higgs particle, obviously, by the time it was discovered, one knew its mass pretty accurately.
Yeah.
And so, but I mean, so far, there are no anomalies that I know of, other than maybe the G-2 thing, which I'm not counting as a
G-2, exactly.
So
your question was, should we build another accelerator? My answer is only when nature tells us to. And I think the only way that will occur is that we pursue precision.
Okay, so I actually have a different point of view to some extent, which is I think there's the possibility of very high energies and very low luminosity. So for example, when you see, right now, the way Accelerator, there hasn't been much innovation in the technology of accelerator building.
Oh God, do we know
for a long time.
Yeah.
Right? I mean, it's superconducting magnets were a big technological thing, but
Yeah.
the basic idea of synchrotrons is the idea that's been there since the 1950s.
Even before, go back to Lawrence Berkeley, right? Lawrence at Berkeley, right? I mean,
right. Building his cyclotrons and things like that.
There you go.
But I mean, so, the thing that I wonder about is if you could just get a very small number of particles at very, very high energies, would there be things that you would see that would be kind of obvious? But I mean, there's a more societal question, which is, okay, you're going to spend $10 billion, are you going to spend it on a particle accelerator? And is it important to physics, for example, that you spend $10 billion on something about physics every few years? Or is that not, how should that work? I mean, in other words, if you say, okay, if we're not building a particle accelerator, we're building a telescope, or we're building a, whatever else. Is that an important thing for the kind of political process of physics or not?
I think the answer is yes, because it's one of the things that you sort of alluded to. If this country is going to maintain a high quality of scientific workforce, that is people capable of doing science at the highest level, the country is going to have to invest in projects that will maintain that workforce. Because if you lose that capacity, it's going to be extraordinarily difficult to regenerate it.
Sure. I mean, it's what one sees right now. Shenzhen is the place in the world where all the electronic innovation happens, and that's pretty much that type of work is pretty much gone from the U.S.
Well, it's like wind power. You still hear people in the United States talking about wind power, but that's gone.
Oh, is that right? Where did that go?
China.
Okay. Is that's where all the big wind
That's
turbines
exactly
are being
right.
made?
That's exactly right.
So how do you think that I mean, thinking from a US point of view, how would you reverse some of those kinds of trends?
So we in the US have a number of fundamental problems as I think about this kind of question. And the first problem actually starts with our education system. Because in the United States, well, look, I tell people, look at me, I have a good tan, right? I'm an African American, right?
Mm-hmm.
And that has implications for the quality of education that people who look like me can obtain. And if you believe in normal distributions, right? If you don't believe in a racist theory that somehow people of European descent are just naturally going to be smarter than people of African descent or Asian. If you don't believe that stuff, which as a scientist I find really hard to believe, then that means that a certain percentage of every kind of demographic of America, you're going to find brilliant people that potentially can make groundbreaking contributions to the benefit of this country.
Mm-hmm.
And so you're handicapping the future of this country by having an educational system that doesn't provide the opportunity in all demographics for the smartest people to emerge, right? You're just handicapping the country. Now, the way that we get around that now is, at least up until quite recently, we welcome people from all over the world. And so we sample these great brains from everywhere else. But now it looks like we're going into a phase when immigration is not going to be welcome into this country. And so that is going to put us into a greater risk. And so I have lots of concerns when I think about how the United States is going to maintain a cadre of people capable of producing extraordinary science, which then leads to extraordinary breakthroughs in technology and ultimately for the benefit of our society. Computers have, right? I mean, look, what are we talking about? We're using information technology. Where did that come from? Well, there were people worried about these things called transistors back in the 50s and 60s, right? So if you don't maintain that kind of long-term commitment, the future looks very bleak.
On this subject of access to education, one of the things that I've noticed, because we run the summer camp for high school students and so on, and in the first few years, we have great students, but they all came from the top schools,
right?
Okay? And then we started pushing, we were running ads in Wolfram Alpha and things like that, and we managed to get geographic distribution.
Yep.
We've not managed to get socioeconomic distribution.
Yep.
And I think the number one reason that I've seen is just, it's like, what do people care about? What do people, it's like, what's the concept aspiration, so to speak? And what's the, it's interesting to hear your own story about, kind of the space-based, motivation for getting involved in science and so on. But I'm kind of curious because, I've gone and visited, rural high schools and things like that. And, it's like, I'm kind of almost feeling like I'm preaching the theory of, science and technology and all this kind of thing.
Yeah.
Nobody cares.
Yeah.
And how does one get around that? I mean, because that doesn't feel like it's an access to opportunities.
I'm looking actually for another, earlier I was struggling to find the right PowerPoint. So now I'm going to find a link and I'm going to tell you a story which I think might help in this regard. So give me a second here. Let's talk while I'm looking. Continue. Yeah. Stephen, your concerns are very valid, and they're the kinds of things that I wish more scientists actually thought about. And that's one of the things that the APS, by the way, you asked what does the APS do? That's another thing that we do, is to try to get our community to connect with the needs for younger people so that we can generate the next generation of us, right? I mean, the whole point is, if you don't have any physicists, you can't have an American Physical Society.
So one of the things I think was a terrible mistake in the American physics community. And one of the things that perhaps even led to the death of the super collider in some ways was the fact that particle physics, to my knowledge, is not taught in high school physics.
That's correct. It is not.
It is in some countries. It's not in the US.
No, it's not.
But I don't know why. Because it's not difficult to explain quarks and how they make protons and things like this.
You could do it like you do chemistry, right? I mean, chemistry gets taught, right? So why couldn't particle physics?
Why didn't that? So I was, I've mentioned this to people at different times, people from around the world, and people say, oh, in my country, wherever it is, Germany, let's say, whatever, well, actually particle physics is in the curriculum in high school. So why not in the US? How did that happen? And how did the physicists let that happen, so to speak?
Well, Stephen, remember, the physicists had lots of money in the 50s and 60s. And so people just didn't worry about that sort of thing, right? I mean, there was money to do fantastic science. There are lots of ideas. Computers came in, first electronics and computers. And so physicists simply didn't worry about the workforce problem, as far as I can tell. I found no evidence of that. So, like I said, I found what I was looking for. So I'm going to try to show you something that I think we could, as physicists, do to make a difference. And it's a little bit along the lines of what you suggested, interestingly enough. So I'm putting a link into my browser.
Do you want to share something again?
I'm going to share something with you. Tell me what you're seeing.
Yeah, I'm seeing the thing about Orange County here.
Okay, so I went to high school in Orlando. I spent all my high school years in Orlando, even though prior to that, well, like I said, got interested in science in fourth grade. I'm sorry, when I was 4 years old, but I was living in Canada at the time. But anyhow, here's a little video. I hope the audio and video works here.
FHIA Remodeling is looking for
commercials, folks. I apologize.
Call right now and get $1,000 off a house full of windows or a new roofing system. Don't wait. It's FHIA Remodeling's window blowout sale. Just call 877-828-FHIA. Call now and save big.
Well, the number of high schools without physics classes has nearly doubled in the last 3 years. For one Orange County high school, student enrollment in physics classes increased by 12 times in just 1 year. Jones High School now has more than 230 students taking physics and 2 full-time teachers in the program.
Next year, every single senior will take physics. Here's how Jones High School is getting results in our schools.
People don't know that physicists do this sort of thing.
Dr. S. James Gates is a world-renowned physicist and a 1969 graduate of Jones High School. He visited with Jones physics students virtually and awarded 2 students $1,000 for excellence in physics.
He gives us a little bit of Jones history and also what physics has done in his life, from going to MIT to almost being an astronaut to doing national commercials.
Allison Kirby is the principal. When she came to Jones High School 4 years ago, the school didn't offer physics, so she made it her mission to find the right teachers.
And she's very willing to help us no matter how many questions we have or how many times we don't understand the work. She is more than happy to go over it.
To see that it's actually reaching them and they're actually able to, you know, solve the problems on their own, it's a good feeling. Even if you go to the medical field, there's biophysics. If you want to go, if you're tired of Earth, you go outside of the planet, there's cosmic physics. It's just basically everywhere. So it's a good science to study.
And starting next year, every senior will take physics.
And I think physics is one of those pathways that people used to see as something that's exclusive, and only the top students ever would take physics. And we really want, by making it the senior science, that it is opening the doors for all of our students to be able to have that knowledge and that access point.
It's an interesting video. So,
Dr. Gates calls the honor that he gives to students an award and not a scholarship. That way students can use the money however they choose. And one of the winners opened his very first bank account with it. And I did speak to him, but we had some audio issues, so I couldn't include that in the video portion, unfortunately, but I will add some more information about him on clickorlando.com so you can read about how awesome their students are.
That's so fantastic. And congratulations for Jones High School for being able to accomplish such a role. And, you know, for people who want to propose physics, physics is that one science which you can actually see, you know, because everything else is a very molecular or a little too kind of, I mean, at least physics, you know, you see friction, you know, you see things. So it's, you know, can you tell I get excited about these things?
Candace is our resident scientist.
No, we always need more. So that's great that more young people are taking it up.
So
nice that newscaster could describe physics like that. That's
but the point is that this is something that I've been doing for since 2004. I got a call from the principal of the high school saying that they were going to give an annual award to the student with the highest grades in math and or science, and that award carries my name. And so I made a commitment right there that every single student who was so designated would get a check from me for $1,000. Now, you know, I tell them, I don't care how you spend it. This is a reward for what you have already done. This is not a scholarship. I would love to see more physicists do this because I think, as you can see, just one person, and that high school, by the way, although it looked very nice, it's in the poorest part of Orlando. It's not in a very wealthy suburb. In fact, there's something called free and reduced lunches, which people may or may not know. It's a measure of poverty. The students who attend that school have the highest number of free and reduced lunches in the Orange County area. So something quite extraordinary has arisen. But like I said, I've been doing this for 15 years. It's something that you do over the long haul. And I think we could make a difference if we actually did it.
So I'm curious about a couple of things. So first point is finding physics teachers. Like, I mean, there've been these efforts like the Math for America thing that, you know, that got done for math teachers and so on. Is it easy to find physics teachers?
It's not. In fact, part of the story that they didn't mention is that the physics teachers that they showed you, neither one was from the United States. They were recruited from another country to come and teach physics.
So, okay, so that, I mean, that's another, for the APS, that must be another issue. I mean, because it's not something people think about as a, you know, there's no kind of, you know, there's no physics for America, you know, teaching program or anything. There could be.
No, Stephen, that's a very interesting way to put it. Even I had not thought of it in that way. But I will from this conversation going forward. Right. I only have 4 months remaining in office. So all I can do is make suggestions at this point.
You launch a little thing and maybe it runs. But so the other thing.
But let me just say, but that story that you just showed, we actually did do that in APS. There's an item in APS News exactly about that accomplishment because I wanted more members to be thinking about this.
So the other thing that was interesting about that video, and which is a very notable feature of physics, physics has been the most successful kind of export field for certain kinds of quantitative people, right? It's, you know, they go on, they do computers, molecular biology, whatever else, right? I actually think physics, one of the things that's happening right now, physics is in the process of losing that position to computer science. and it
Yeah.
shouldn't. But part of the reason that that's happening is that, you know, computer science has been in many ways a very you know, it's about writing code and things like, in many places just about writing code and so on. But the question for physics is what counts as physics, and the narrower that is, you know, the less successful physics as an ongoing export field will be. And so that's something, again, for the physics community, I think that's a question. You know, is you know, I don't know, from back in the day, you know, there was the whole econophysics thing, or there are these questions about, you know, is the study of machine learning, is that, you know, is that physics?
Yeah.
Or is that, and, you know, in a lot of things I've done in exploring kind of computational universe of programs and things like that, most physicists would say that's not physics. We don't know what it is. It's not mathematics. It's probably not computer science, but it's not physics for sure.
Well,
And,
I agree with you, Stephen. People tell me I'm not doing physics, right? I'm
Right.
wondering about supergravity, which is a physics problem. I'm doing it in ways that are not traditional tools, and people say, well, gee, what is it that you're doing? It doesn't look like physics to me.
right.
So this is a problem that our discipline suffers from. Let me just notice in the note in the chat that some interesting comments that people should observe. We talked about the SSC, and one of Matt, I can't quite, Kafker, I guess is the last name. Matt points out that Phil Anderson's testimony against the SSC contributed to the demise, and he's quite right. There were a group of condensed matter physicists who were convinced that if they could kill the SSC, money would flood into their parts.
Yeah, that was just a disastrous.
That was just, it was one of the most naive, incredible things I have ever seen physicists do.
What were they going to spend $10 billion on condensed matter?
That, you know, it's like the dog that chases the car. What's the dog going to do when it catches the car, right?
Uh-huh. Yeah, no, I mean, that was definitely a low point in terms of physics. But I mean, I am curious for this kind of concept of the definition of physics for, you know, I mean, as far as I'm concerned, a lot of things I've done, I'm perfectly happy. I mean, I've never really wanted them to be physics. That's why I wrote a book called A New Kind of Science, is because that's what we're kind of trying to carve off. But, you know, I remember when I was working on that book, a friend of mine said, why don't you stage some kind of leveraged buyout of physics? What he meant by that was that physics has all these institutions, it has all this structure, it has lots of smart people, and at the time, as 20 years ago, it seemed like a lot of things had lost their way. And, you know, there's a question of, okay, if you can, you know, inject new intellectual direction and you've got this institutional structure, you know, what can you do with it? And so I'm curious, you know, the APS has been around, 100 years or something now. And the question is, you know, what do people imagine the definition, how will the definition of physics change over time? Is physics basically the study of differential equations and how they work in, you know, I don't think you think that. I don't think.
You know, I don't think that.
Yeah, right.
I think that there is, I think there's an openness that, at least certainly among younger people coming into the discipline, to be much more broad-minded, to think about where the boundaries are, and in some sense to make the boundaries irrelevant. Remember I talked about my summer program, and we were comparing the days to start.
Uh-huh.
The young woman, there was a single undergraduate in that program. She, as I said, I would describe her as an analytical neurobiologist, and she's had some success. Her name is Karina Kurto. Everybody wants to look her up, and she attributes her success to the fact that she thinks like a physicist. Uh-huh. So this gets back to your comment about physics being having an excellent history of exporting people that can have unusual impact far outside of the boundaries of physics, right?
Right.
And so, as I said, my sense of the organization is that people understand that. Maybe some of our more mature members aren't on board, but since the younger people are going to ultimately take these positions, I'm very hopeful that the APS will continue. In fact, right now we have a campaign to make sure that the word is out among what people have traditionally called industrial physicists, right? People who go into the business world, the corporate world.
Yeah, I don't know. Do I count as an industrial physicist? I don't know. I'm not terribly industrial, but
well,
I'm
actually,
quite
I
a
don't.
physicist,
Well, actually, I don't like the term because I think it's too limiting. I would prefer the term corporate physicist because that's a broader definition of people out in entrepreneurial activities applying physics to solve real-world problems. When you say industry, to me that strikes an image of factories and forges and blast furnaces, and but that's not what industrial physicists actually do mostly. There's much more.
I think maybe a better term would be private sector physicists, because actually it's not even clear, corporate. I mean, the number of people who have job title physicist at companies. It's an interesting question where they are. The APS should know that. I wonder if the APS knows that. In what kinds of companies are there people with job title physicist?
You want to come join me and talk to my colleagues?
Not my scene. I do horribly in those things. But no, I bet that, for example, an interesting question would be, if you look in Silicon Valley, for example, how many people outside of sort of instrument makers and so on, are there any people in, who have title physicist, for example? I don't know.
Yeah, I don't either. I know who I can ask to find the answer to the question.
Yeah, I mean, it's just, but it seems like that's this question about sort of where do the physicists go? I mean, I would have thought if I was, okay, now I'm being, if I was thinking about the APS, one of the first things I would do is try and map out where do the physicists go, and maybe that's been done. I mean, that is even just at the level of, you got all these members, people who joined the APS at some time, where did they go to work, all those kinds of things.
I'm very familiar with the concept, but interestingly enough, not from my work in the physics committee, but from my work in advising President Obama in the Ed department, because there are studies that those organizations do. They produce these beautiful charts. You've probably seen them, where one way to show the information is in the form of a circle, and then you put lines in with designations of different endpoint designations and
right.
Academic streams in college. They're quite interesting. I've never seen anything done like that in physics.
I think I've seen the National Science Foundation has produced reports like that about the U.S. workforce and so on.
That's correct. That is exactly the ones I'm thinking about. And so has the Department of Education, by the way. But I've never actually seen anything like that for physics.
Oh, well, it's a bit of homework there for the...
Yeah, it is.
Anyway.
I hadn't expected that you would give me homework assignments.
No, I wasn't intending. Anyway, we should probably wrap up because we've gone quite a lot longer than we said.
It's almost 5.
But
and we didn't actually get to the issue of, well, the thing I had wanted to present to you was, so for SU3 I showed you what the raising and lowering operators do.
Uh-huh.
I didn't get a chance to share you that story about adinkras, and we spent so long talking outside of physics. You're going to have to invite me back sometime.
Yes, that will be a pleasure. Yeah, right. It's all right. We should wrap up here. But
okay.
So thanks very much for
That's been fun, Stephen.
joining us, and see you the next time.